Welcome to this lecture on power quality. So, we like to cover today this active shunt compensation. Last lecture we covered active passive shunt compensation. So, this active shunt compensation we already discussed in introduction, typically consists of basically D-STATCOM. It is also distribution static compensator, in short we call it D-STATCOM. So, we like to introduce this today. We will like to talk state of art on D-STATCOM, distribution static compensator. We will classify of this D-STATCOMs, and we will discuss principal operation and control of D-STATCOM, because it is active compensation. So, control is also becomes important. In passive compensator there was no control, but here we have a control. So, we like to have a then analysis and design of D-STATCOM. We like to then again model and simulate and give the performance of D-STATCOM, then followed by the numerical examples, and we like to summarize with the references like. Well, so the objective of this is the requirement and applications. We like to discuss where the D-STATCOM are needed and where are the applications, and we talk to this configuration of active shunt compensator and control of active shunt compensator and analysis design of active shunt compensators, and we like to have a method of modeling and control of this active shunt compensators like. Well, the power quality problems in distribution system, we have a two kind of power quality problem. One is voltage power quality problems, we discussed in the even introduction and earlier lecture, like typically like a voltage sag, swell, voltage unbalance and free current tangent, an example. And current power quality problems are like a power factor, like a voltage regulation problem, unbalanced current, excessive neutral current, and if there are harmonics, then harmonics also like. But here we will not like to consider the harmonic in typically D-STATCOM, we will cover that into later on in active shunt filters like. So, the solution for these, we call it the custom power devices. We also call them custom power devices like D-STATCOM, distribution static shunt compensator, DVR dynamic voltage restorer, and UPQC unified power quality conditioner. So, current based power quality problems, the solution is D-STATCOM, a distribution static shunt compensator, which we like to discuss today. And to give you an example, through technical, this is the typical photograph of a, you can call it of D-STATCOM of 2 MVA with which can have a plus minus 1 MVA and install in Hammond substation. To give you a confidence like the pure wave have manufactured this D-STATCOM distribution compensator up to 6 externally switch capacitor or reactor bank can be controlled by pure wave D-STATCOM, and we like to discuss. So, that is why just to give you idea that some manufacturer are already manufacturing this D-STATCOM. So, it is not a really new thing, it is already used in practice. So, we like to discuss on state of art on D-STATCOM. So, now D-STATCOM topology, you can call it technology, is the mature technology for providing compensation of reactive power, providing the load balancing and providing the neutral current compensation, and if required we can have a harmonic compensation also. You cannot say if there is a harmonics then we will not compensate, but certainly this if you compensate harmonics that will add the extra cost as well as size and weight of the this D-STATCOM system like, because switching frequency have to be increased, because in case of your only sinusoidal and typically your typically only the sinusoidal environment with the passive impedances or kind of, if you do not have a nonlinear load, then in that case you will have only the to have generate like only fundamental frequency currents for all these compensator, whether for reactive power, whether for load balancing or neutral current compensation. Well, D-STATCOM are also used to regulate the terminal voltage and to suppress the voltage flicker in kind of fluctuating load like furnaces or other applications, and to improve the voltage balance in 3-phase systems like, of course, if voltage balancing tendency is there if you really compensating the load in shunt like. And classical technology for meeting the power quality, earlier what we were using in place of that, the power capacitors, in static we are compensated using thyristor control reactor and thyristor switch capacitors. That was the earlier at least, and that is still used in the case of transform, you can say very large rating transmission system. But the right technology here is the mitigation by D-STATCOM. The reason being the power capacitors can give you only leading reactive power, but D-STAT can give you the leading as well as lagging reactive power, and D-STAT can generate even the can compensate negative sequence current where the passive element like cannot give you the contextually variable load balancing features. It can be only designed for one fixed kind of the load, like that is the reason the D-STATCOM is the right technology for all this compensation. Like, so the coming to the development, there are varying configuration according to the application requirement, and there are advanced control strategy because this is an active device. So, we have to put a control algorithm for typically control of these D-STATCOMs, and of course, the what devices you are using into this, like devices in the sense we talk about like which configuration you are going to use, like whether you are going to use like a typically like a very low rating like a MOSFET, medium rating like a maybe IGBT kind of, and then the another responsible technology is the sensor technology. We have to sense the signal like a current signal and voltage signal. So, for that we have a Hall effect voltage and current sensors, like your current transformer and voltage transformer cannot give a very fast response, which you require in these for feedback. Like, the another reason for development have been the microelectronics revolution. We have very fast microcontroller and DSP, digital signal processors, for typically for for the control of this, like typically, and now their cost is reducing day by day. So, it is practically possible to implement all these algorithms in the microcontroller or DSP, like of this D-STATCOMs, like. And of course, for the research laboratory environment, we have a DSP which is like a D space, maybe microlabux 1202, and we require the voltage source converter or this voltage source inverter, and then or you can use the DSP, like. So, some of these are used in laboratory environment, but when it goes to the industry, of course, you have to use the inverter, but which is more compact, and apart from that you can put the entire into the simple microcontroller one PCB, not to have such a large size or so. So, that is about the little bit implementation aspect. Coming to the classification of D-STATCOMs. These STATCOM can be classified into many ways. One is the converter use. So, we can use the current source converter bridge structure with the pendulum control. Of course, with the IGBT. Nowadays, invariably we are using IGBT, where it can go reasonably switching frequency, which we expect in this case. Or voltage source converter, the bridge converter. Well, the voltage source we will discuss with the circuit, like why voltage source converter have taken a lead over the current source converter for use this in these applications like D-STATCOM. Another is typically the topology, whether you like to use the transformer for interfacing this D-STATCOM with the grid network, because sometimes we need the transformer for many purpose. One very purpose is the isolation, another is that you like to use the D-STATCOM at high voltage network. So, the power electronics may not be a optimally designed at such a high voltage. So, we can use the transformer in between to transform the appropriate voltage at which the power electronics converter or let us say interface with the transformer. So, there we use the transformer like a typically high voltage, maybe like a traction application. Few examples I can mention it, or in the industry of very high power rating. But in normal distribution system, we can avoid the transformer because it extra add the cost as well as the weight. So, if the voltage is not to be stepped large, then there is no need use of transformer. So, there are transformer less configuration, and then there are various arrangement of voltage source converter. In a sense that you can use like a typically in case of 3-phase 4-wire system, either you use of single phase unit or you can use the 3-phase itself voltage source, and 4-wire system you can use typically even a 4 lag voltage source. So, we will discuss all those. So, that is a kind of classification. The another classification is on the basis of number of phases, like whether your typically it is a system is of 2-wire single phase or 3-phase 3-wire system or 4-wire 3-phase system, like also. So, that is on supply based classification. Because your if supply let us say load is only single phase, so you need the single phase D-STATCOM, it is a 3-wire 3-phase system, then you require a D-STATCOM also for 3-phase 3-wire system, because you might have to compensate like 3 in 2-wire system single phase system like a kind of reactive power you will like to compensate, and in case of your 3-wire system you will like to not only compensate for reactive power, but you will like to compensate your unbalanced current or negative sequence current, and 4-wire system you like to eliminate even the neutral current along with your reactive current, reactive power and the negative sequence current. So, you like to do neutral current compensation also. That is the difference in the typically. So, coming to first classification on converter based classification. So, you can use the current fed or current source fed D-STATCOM. In current fed you can see the of course, the supply with source impedance connected to the consumer load, and you have this D-STATCOM made with the let us say the current source converter, and current source converter even if you are using let us say self commuting device like IGBT, you need the series diode. The reason being current source converter needs the negative voltage blocking capability, and for negative voltage blocking capability I mean the IGBT do not have, so you have to connect a series diode which can withstand for negative voltage across the total switch like I mean also. And on the DC link side you require energy storage like a current source. So, that can be realized with the help of an inductor across the DC link. Of course, it can be you can call it current in the inductor can be controlled well in self control manner, and we do the self control voltage for the case of shunt compensator. Here the problem is on the output of this converter you will be generating PWM current, and these currents PWM current segment of the DC link current, and to make this current continuous. So, we need the shunt capacitors which is mandatory here in that case. So, the major difficulty of course, here are one is the on DC link you need the inductor which is costly, noisy and lossy and weighty, and another is then when switch conduct you have a drop of IGBT as well as diode. So, you have a loss in the switch also which may be 1.5 times to 1.5 to twice the switch which is used in voltage source converter like and then this capacitor is also mandatory shunt capacitor on AC side, you cannot eliminate this also. So, you can call it like you are going to add a such a element which increases the cost, size, weight and losses also, and the response is also not so fast because of you are putting the inductor on the DC link like. So, in place of this for providing same compensation we can provide the typically voltage fed or type of D-STATCOM where voltage source converter is used for as a D-STATCOM, and in this case typically on DC link you have electrolyte capacitor which is cheap, lighter weight and cost effective and lossless, loss also less in that case. And then you have a IGBT switch with the anti-parallel diode. So, here in this switch when it conducts either IGBT will conduct or diode will conduct. So, you will not have a you will have a lower losses in the switch, and similarly on the other side you have a interfacing inductor, you do not have a like a parallel shunt capacitor here, and this inductor capacitor even if you are using a transformer because of application requirement, then this inductor can be also avoided, that transformer leakage reactance can be adjusted to take care of this your inductor. So, that element also get reduced, either you can use the reactor or you can use the transformer, any one of the two in that case. So, this here the losses are also less on the DC link element like in a capacitor, the device switching losses are also less, device conduction losses also less, and then of course, the element which was in shunt capacitor in case of current fed which is not required. So, that is the reason this voltage fed or voltage source converter in D-STATCOM had taken a lead, and commercially these are in practice like. But of course, as far as the research equivalent concerned, that also can do the job. But out of the two options you consider the best option which is best for you like. So, this voltage source converter fed D-STATCOM is considered to be the better than the previous one, and it is used in practice like. So, that is about the converter based classification. Now, we come to the supply system based classification. The supply based classification can be like a single phase, like a 2 wire D-STATCOM for single phase, as you see the single phase circuit here. So, we can we can either have a current source converter. So, giving you idea that how can current source converter can be there, used as a D-STATCOM. So, you have a 4 switches here with the bridge, and on DC link we have a typically a inductor here to derive a kind of a current source or constant current in the inductor, and well we operate these switches in PWM. So, when switch operate you can call it like a typically here the IGBT and diode both are in series, so losses of both are there, and then you have to use a shunt capacitor, so that the net current sum of IC plus ICC that remains the continuous like or so. So, this is the current source converter base, just to give you idea how it look like the D-STATCOM for typically for single phase configuration like. Then this is the voltage source converter, like you have after source impedance, a single phase as bridge, voltage source single phase your voltage source inverter with the interfacing inductor, and then a small capacitor. This small capacitor is a part of a filter, and why we connect this after LR this CR, the reason being the converter will be generating the PWM voltage at the output of AC terminal of this converter, and this PWM voltage depending upon the source impedance, this LR, this is the interfacing inductor cannot absorb all the ripple, because the supply voltage is somewhere buried into the system. So, you will find if source impedance is higher, you will find a COM across the typically across the load. So, to eliminate those all voltage higher voltage ripple, I mean if you put a small value of CR, I mean just like as a ripple filter, we assume that the impedance for this even a value of capacitor is very small, hardly order of like a typically of 5 microfarad. You will find the impedance for high frequency switching around switching frequency are higher than that, you will have a very low impedance. So, it will absorb I mean all those harmonics here, and typically it will like a we have a short circuit for higher order harmonics. So, entire ripple voltage have to be absorbed now across the inductor, and for fundamental frequency this capacitance will be have very high impedance. So, it will not draw any fundamental current into the capacitor, will be very small. Even sometime we put a small resistance, damping resistance also in series with the resistance. So, losses also negligible in that case, like, but improve the voltage profile at the point of common coupling, which is of course because of the switching of this converter, like I mean also. So, that is a voltage source converter, I mean based D-STATCOM for single phase system like also. Well, for coming to 3-phase 3-wire system, I mean we have a plenty of topology. So, here is the classification for 3-phase 3-wire D-STATCOM. So, either we can have a non-isolated topology of voltage source converter. I mean now we will like to confine voltage source converter only. So, we can have a 3-leg voltage source converter or 2-leg with the split capacitor, I mean like on the DC link. So, that also people have tried to use in very low rating, or you have a isolated voltage source converter, which I talk about. You use the transformer for isolation when you really want to interface to a high voltage system like a traction or railway, I mean for the D-STATCOM use in there, because the at substation you will have a quite high voltage. I mean even on the secondary side you will have a 25 kV, primary side you might have a 33 kV or even much higher than that. So, you like to interface such applications on high voltage, then you need the transformer. Maybe power electronics is designed at optimum voltage at which the cost of the total power electronics is quite low. So, in this case you can use the 3 single phase voltage source converter, I mean like 3 edge bridges, or you can use the star delta transformer with 3-leg voltage source converter, or you can use a star delta transformer with 2-leg voltage source converter. So, you have a like a typically options around like a 5 options, and it depends on application requirement which option is suitable to you, I mean like I already mentioned. So, consider this typically 3-leg voltage source converter. I mean you have a typically a 3-phase supply system with 3-phase load, and we have a 3-phase voltage source inverter here with interfacing inductance, and at the point of common coupling which we are showing there we have a this ripple filter RF and CF, which is responsible to eliminate the voltage ripple generated by at the common coupling by this voltage control, I mean this voltage source inverter by switching like, and the DC link voltage across the DC link capacitor VDC we have to regulate of course to a constant value, reference value, otherwise this converter will not operate successfully as a 4D STATCOM operation. So, this also we have to control, I mean by taking a little extra power from the same source for meeting the losses of this entire system, in the sense losses in the interfacing inductor, losses in the switching devices, dielectric loss in the capacitor. So, that we will discuss in the control in detail like I mean, but you can understand the ripple filter is required for improving the voltage profile at the point of common coupling. Otherwise, we do not know the impedance, because the whole I mean source is somewhere like a VMA. So, you can call it the entire difference in your this PWM, I mean will be absorbed the source impedance and this LR, and if LR is we cannot increase beyond a certain value, because it will increase the cost, size and weight. Apart from that, it will not allow to change the current very quickly. So, there is optimum value of LR we will like to discuss in the design. So, if it cannot increase to higher and source impedance is high like a VKC grid system, then this ripple filter play a very important role in the design or operation of this D-STATCOM like. Well, the another topology which normally can be used for low power rating, people have mentioned in the literature that you can have in place of 3-leg, you can have a 2-leg, and 1-leg you can take from midpoint of the capacitor. But here there are typically 2 disadvantages of this topology. It cannot be used for high power. The one reason being that these you have to use 2 capacitors now in place of 1 on DC link. So, for deriving the midpoint. Another major drawback with this is these capacitors should be able to take the entire ripple current or entire fundamental current even which is flowing into the typically 3rd phase. So, that is another drawback. So, size of the capacitor further increase. This is only preferred for lower rating, but otherwise I mean we prefer to like a 3-leg previous topology like I mean also. Well, we can use, if we use the transformer isolation, I mean which is given here, we can use the I mean if transformer used for isolation, then we can use the 3 edge bridges for 3 phases, I mean with transformer isolation. I mean, this really give a very specific advantage. Of course, we have to use the ripple filter. This LR need not to be now separate. It can be as a leakage reactance of this transformer, and the H bridge have a very specific advantage now. With the you can have independent control of each phase current, and now you can use the unipolar switching here. Unipolar switching, or you can give a benefit is there that the switching frequency can be reduced to half compared to the ripple frequency of the current which is going through the LR. And moreover, the DC link voltage also reduces here, I mean much lower than even for unity. You put a unity gain turns ratio transformer, even then DC link voltage can be reduced to much lower, like in the previous first topology. If you are keeping like a 700, it can be put only 400 volt. So, device voltage rating also can be reduced, even the transformer is used with the your unity turns ratio. I mean the voltage rating of the all the devices can be reduced, as well as the your voltage rating of the capacitor can be reduced. So, that is a specific benefit, but the disadvantage that you are using a transformer, if it is not required, I mean provided if some application require transformer, then you can take the benefit of it. Another is that in place of 6 devices you are using a 12 IGBT here. So, that also another, you can call it the drawback of this. But of course, if we needed isolation, you are integrating this your D STATCOM for very high voltage system, certainly this circuit have a many advantage compared to the other topology. Then you can have this even the isolation with the simple star delta transformer. There of course, you know to have a 3 single phase, but you can use a 3 voltage source, 3 phase voltage source, 3 lag voltage source converter, and that also can serve the purpose as far as the you are integrating to this to high voltage network. I mean with taking a power electronics part on at appropriate voltage on low voltage, and this LR just it is shown symbol, but it can be like a leakage reactance of the transformer. I mean take care of this your interfacing inductance like also. Well, we can have a like a now isolated single H bridge in this also. In place of 3 lag we can use the 2 lag, but I have already mentioned the drawback in case earlier also that you require 2 capacitors to derive the midpoint, and secondary advantage that entire third phase current flow through these capacitors. The capacitor value should be very large. So, certainly it is not preferred for large rating like I mean also. So, these are typically the topology of 3 wire system. Coming to the topology of 3 phase 4 wire D STATCOM, you can see the large number of topology. I mean here for 3 phase 4 wire D STATCOM. So, we can have a like a non isolated topology. You can use a 4 lag voltage source converter or 3 lag with the split capacitor, or you can use the 3 lag voltage source converter with 3 DC capacitor. We will discuss with that, and we can have a 2 lag voltage source converter with the transformer isolation, different transformer isolation, or 3 lag voltage source converter which can be normally practically used with the different transformer isolation. And transformer isolation can be like a zigzag transformer or star delta transformer, star hexagon, T connection, scout connection, and star polygon connection. What I mean, the transformer can be 3 phase transformer for used for isolation can be connected without isolation can be connected here for the purpose here with the 3 lag or 4 lag here for 4 wire, because that can have a neutral current compensation also in this 4 wire system. Coming to isolated topology, we can have a 3 phase VSC, or we have a 3 lag VSC with this transformer connection, considering the neutral current is taken care by the transformer itself, and then 2 lag also we can use by that, as we already discussed here with the transformer connection like I mean isolation. So, all these transformer provides wherever the topology are there, virtually it provide the sometime the neutral current compensation as well as it provide the isolation also. So, we would like to discuss some of the topology there with the circuit configuration. So, this is the first, we call it very normal configuration which is normally preferred to use. It is a 3 phase 4 wire topology. So, for 3 phases we use of course 3 lag, and one additional lag we use for neutral current compensation. As you can see typically of it is written here, or the 4th lag where also interfacing inductance sometime it is different, it is not equal to all LR, it can be LRN or so. And so, this responsible to compensate neutral current locally, so that supply current ISN can be made 0, because there may be load unbalanced load. So, the negative you can call it neutral current for the load can be compensated locally, it is not necessary to flow into the grid, but you want to realize this as a balance. Typically the balanced load after the compensation, even with it is unbalanced load and having a neutral current. So, once you have a balanced load, unity power factor load, then the neutral current can be made 0, even for voltage regulation and balanced load you are using that, in that case neutral current also will be 0. So, 4th lag is used for basically neutral current compensation here like so it does not need the transformer. So, it is a very economic configuration and you have to regulate the DC link voltage for, you can call it like a for self supporting DC bus by control. We will discuss this control little later on. This is another configuration for 3 phase. This configuration we have shown earlier also, but now we are using like a 3 phase, 3 single phase with the transformer isolation, and but the inverter all 3 legs, all 6 legs are connected. So, that you can save the one way that you can have a 3 single phase inverter with separate capacitor, or you can have a on one capacitor on the DC link. It really certainly will help to reduce the number of components, like you can have a only one capacitor here, and you have a independent already earlier also we discussed independent control of all 3 phases. So, I mean with the star connection of the grid side, I mean you can have a neutral current compensation also here, as it is the your star point connected to the neutral, I mean of this of second in the sense on the which is on the grid side also, and power electronics cost here also you can design the power electronics at appropriate voltage, optimum voltage at which the cost of power electronics is low, I mean like also. This is another topology. Of course, you can have a 3 leg with the midpoint capacitor, which takes the responsibility of your neutral current, but the again reason is the entire neutral current will be flowing through, even that can be even a fundamental current as a maybe unbalanced load. So, entire neutral current, one is that you need the 2 capacitor, another is to derive the midpoint, and another disadvantage that the entire this neutral current have to flow through these capacitors to go to the circuit like, I mean. So, certainly it is not certainly preferred for high you can call it power rating, I mean like. The another connection of course, in like a developing country we consider it that for 3 phases you can use the 3 leg voltage source converter, and then for neutral current compensation you can use the zigzag. Because zigzag connection is quite effective of the transformer for eliminating the neutral current or deriving the local neutral, I mean like. So, here that is the reason what we are connecting here the zigzag transformer for neutral connection. The only typically disadvantage that the transformer is little bulky, I mean compared to like you could have taken a one more lag, but of course, sometimes the inverter cost is high, that is the reason it is considered. Of course, the another benefit of this of I mean even neutral is not there of the supply, still you can get a very stable neutral for the load side. I mean if neutral is also neutral conductor busted or isolated, you can have a stable neutral for your load. So, load will go on experiencing the here itself the stable neutral also with this zigzag transformer. So, that is not only purpose that is really share along with your D-STATCOM, but it also serve the other purpose like or you can have a like a typically a for this typically neutral current compensation you can have a star connection and closed deltas on the secondary side. But of course, the disadvantage compared to zigzag of this is that you have a losses in the typically on the star side as well as in delta loop also, which where the your 0 sequence current or this your neutral current will be flowing into that like or you can have a typically in place of the your zigzag connection for neutral current compensation you can have a T connection, T connected transformer, I mean. So, that also can provide the purpose of that like or you can have a typically your star connection with the hexagon for closed path. You must have a closed path for neutral current compensation, which is normally otherwise you might have seen that normally in distribution transformer on the supply side we connect delta loop for providing the and the secondary side we have to connect the star because you need the neutral terminal for providing the connection for you can call it the for single phase load of the I mean the consumers like. So, similarly you can have again T connection, Scott connection also. Scott connection is quite famous connection for converting like a. So, here also Scott connection also can eliminate the your neutral current like I mean also. So, we have a without secondary 3 connection like a T connection, Scott connection, and typically your zigzag connection also, and of course, you can use the 3 leg or you can typically take a even a 2 leg also. So, these are the typically important connections or configurations of your typically of your D-STATCOM. We have considered single phase, we have considered 3 phase 3 wire configuration and 3 phase 4 wire configuration like. There may be many other configurations which are reported, but these are the kind of important one or which the industry I mean which are used in the industry like I mean also. Well, the as far as typically we go to principle of operation of D-STATCOM, the main objective is the mitigation of current based power quality problem by compensating typically the reactive power, unbalanced current and neutral current, and typically the harmonic effort is required, and then of course, the typically fluctuations like. So, result in after putting a compensator with proper control, it should result I mean the sinusoidal balance current in the supplied and with the DC bus voltage regulation. DC bus voltage regulation for all these STATCOM configuration is the mandatory requirement, otherwise the STATCOM PWM will not function properly like I mean. So, well, we can call it in general a DStatCom has a voltage source converter connected to DC bus and AC side of it connected to the shunt, normally connected across the consumer load or across the point of common coupling, and these voltage source converter use the pendulum control pulse width modulation control. Therefore, it requires a small ripple filters to mitigate the switching ripple like So, well, DStatCom implementation or the circuit require the Hall effect voltage and current sensor for feedback signal for the control of this, and digital signal processor or maybe you can call it DSpace is one platform. There may be any platform like our microcontroller is used to implement the required control algorithm to generate gating pulses for the solid state devices of voltage source converter of DStatCom, and the voltage source converter is normally controlled in pendulum current control mode to inject the appropriate currents in parallel in the system. Another requirement is a DC bus capacitor, a AC inductor, we already discussed it, and injection and isolation transformer and a small passive ripple filter like The typical photograph of DStatCom which we have in the our student implemented in the laboratory, and this is the sensor voltage sensor board which we have used in implementation. This is the circuit of typically of sensing circuit of this voltage source, Hall effect voltage source in Hall effect voltage sensor, and this provide the isolation from high voltage to low voltage, and this after that low voltage virtually we have to scale up and filter it the noise out of it, and then put appropriate voltage which are accepted by DSP, because some DSP accept only typically your 3.3 volt, some accept plus minus 10 volt. So, accordingly you have to scale up with the scaling, but you have to keep in this mind you have to use the operational amplifier which are enough fast slow rate. You cannot use the slow amplifier. So, LF353 have a very fast slow rate compared to your normal operational amplifier of your typically of 741 or so. So, 741 cannot be used in this case like just to as a feedback like. This is the current sensor, alpha current sensor PCB. There are lot of kind of current sensor. This is maybe a PCB mounted up to 25 ampere. This typically like a 50 ampere current sensor, but you might have a 300 or 3 kilo ampere depends on the rating, and there the thick wire which are going through it, it is power circuit, and on secondary side of course, we have a complete circuit which give a sense signal to us like So, here also you have a LM current sensor, and secondary side we get the signal across this RM, we get the voltage when current flows, secondary current flows through this, and this current signal which is converted into voltage signal, now we have to scale up, which can be given to ADC analog to digital channel of the processor, whichever processor you are using, whether DSP or DSpace or any of the processor you are using. So, this is like a sensor circuit like The design of distribution static capacitor, in short we call it DStatCom. Well, to start with, we will like to discuss the design of 3-phase 3-lag voltage source converter based DStatCom, and we already discussed the circuit that it consists of 3-phase supply system and the typically 3-phase load, maybe unbalanced load, maybe balanced load. This load have to be like a 3 wire. So, you can, and then we have a typically a DStatCom with the 3-lag voltage source converter, and we have the DC link capacitor and ripple filter which we discussed earlier. The very role of typically of DC link capacitor is to provide the self supporting bus with the proper control, and if DC link voltage is maintained appropriate, which should be peak of more than the peak of the line, we will just discuss with the design formula. Then to maintain this, then only it will work with the proper pendulum control to inject the current at the point of common coupling through this inductors like So, the purpose of inductor is because on the inverter side you have a pendulum voltage, on the grid side you have a typically balanced sinusoidal voltage. So, it should absorb the difference between the pendulum voltage and your typically the point of common coupling sinusoidal voltage. The very purpose of ripple filter, we discussed this RF and CF, is to improve the voltage profile at the point of common coupling, because the voltage at the inverter output is pendulum voltage, and we do not know the source impedance. If source impedance is higher, this inductance interfacing inductance LR will not be able to absorb all the ripple between the difference between pendulum voltage and typically on sinusoidal voltage. So, you will find a kind of high frequency comb of around of switching frequency at the point of common coupling. To reduce this switching ripple voltage at the point of common coupling, we use this RC filter. The value of RC filter we will discuss it. At high frequency, this impedance of this will be almost closer to resistance, which is we normally select order of 3 to 5 ohm, So, it should be order of that. So, it means and it will provide the short circuit for high frequency switching harmonics, and the capacitor value normally we have order of 5 microfarad. At switching frequency it offers very low impedance, order of very close to resistance, but at fundamental frequency it offers very high impedance, order of 300 ohm, and the current even with the 300 volts at the point of common coupling of the it does not draw the current more than 3 milliampere at typically at fundamental frequency. So, the losses in this hardly may be less than 1 watt irrespective of the rating, I mean typically in this ripple filter like on. Of course, the load can be your balanced load, unbalanced load, reactive load, may be capacitive or inductive in nature. So, variety of load which we are going to compensate. So, after compensation from the DC STATCOM we expect the supply current or grid current should be sinusoidal balanced and preferably either at unity power factor, or we can use it for, if we are using this DC STATCOM for power factor current, so those currents should be in phase with the point of common coupling voltage. So, whatever the requirement of the load is there, whether it is reactive power, negative sequence current or unbalanced current, okay, it is taken care by the typically by this DC STATCOM. And the selection requirement we will like to discuss here, a DC link capacitor and its voltage rating and interfacing inductance value, injection and isolation transformer if it is there at all, and then we will like to discuss a small ripple filter like. Well, to select the DC link voltage, I mean in this the relation is really from voltage source inverter. You may find in many of the textbook this relation, I mean which is where M is the typically where M is the modulation index of the inverter and is considered 1, I mean like you can take accordingly the safety factor, and VLL is the line voltage in RMS at the AC line voltage at the point of common coupling, and thus this DC link voltage is obtained from this relation. If you keep the value of typically of VLL 415, it comes around 677.99. So, well, to round off little higher, as we have taken modulation index 1, then it can be rounded off to 700 standard voltage like of 700 like I mean or so. So, that is about the selection of DC link voltage. I mean it should be greater than the typically of the peak of 415 is around like typically 586. So, it is on 700 side is slightly, because what is supposed to take care, it is supposed to take care the drop of the both the inductor of the line which are interfacing inductor we discussed last time from the circuit, or just previous slide we have discussed it, and of course, it had to take care of the modulation index, and it had to take care of even there is a variation in supply voltage in place of 415, it can go even a 440 also, still the inverter should or voltage source converter should operate satisfactorily like I mean also. Well, as far as selection of capacitor is there are many criteria. I mean these are virtually the design guideline we consider it. So, one of the criteria is that you must not have a ripple voltage, I mean corresponding to the harmonics, I mean you might have a lowest second harmonics. So, that is one criteria. So, corresponding to that there will be a ripple voltage, we will discuss that also, but the very important stringent requirement is the dynamic variation of the voltage. The relation which is given here, it is half CDC I mean into VDC square minus VDC 1 equal to K1 into 3 V, that is the phase voltage, and AI. AI is the coefficient, we will discuss that, I and T. T is the time period in which we want to recover the voltage back at the nominal value of VDC. I mean if it is deviated from, let us say from VDC to VDC 1. This VDC 1 may be the lower voltage or it can be higher voltage, accordingly we can select it. So, based on this relation of energy, you can call it energy storing and energy conservation formula, I mean we just decide the value of capacitor. So, where here the VDC is the nominal DC link voltage to the reference DC voltage, and VDC 1 is the minimum voltage level at the DC bus, and A is the overloading factor, and V is the phase voltage, I is the phase current, and T is the time by which the DC link voltage is to be recovered. So, considering the minimum voltage level of the DC bus, that is typically 677.69 and VDC 700, and considering phase voltage RMS 239.6. So, I mean like corresponding to the rating, let us say it comes 76.51, and T 30 millisecond we want to recover the, and A is the safety factor maximum allow current, let us say 1.2, 20% more means 1.2. The variation of energy dynamics will be 10% corresponding to K1 equal to 0.1. Then the calculated value of this DC link capacitor comes around typically 12,852, and we can select around 13,000 microfarad, little higher than that for a typical Givering rating. So, that is the way how we can decide I mean design the value of the capacitor from this relation like also. Well, the interfacing inductance, I mean like this is LR what we already discussed it. I mean this is corresponding to the ripple current, how much ripple we want to allow virtually from the inverter to go in the inductor. So, this is the relation derived for 3 phase, I mean where the root 3 is the corresponding to typically the line voltage and M is the modulation index and VDC is the DC link voltage and 12 is the factor corresponding to 3 into 4 virtually and F is the switching frequency, A is again the overloading factor and ICR is the ripple current like percentage actual ripple current like how much as a percentage of the your DC STATCOM current. So, M is the modulation index and A is the overloading factor considering the ripple current of 15 maybe 15 to 25% is the standard ripple current and switching frequency may be even if we are doing only the compensation for reactive power and negative sequence we can take low frequency at around of 1.8 kilohertz, but if we are doing harmonic compensation then certainly the switching frequency should be at least double the lowest harmonic we want to compensate. That we will talk about somewhere little later in active shunt filter again and VDC equal to 700 and A equal to 1.2, the value of this LR is calculated of 4 millihenry. So, round off value of I mean it comes typically 3 point something and then rounded value can be taken up as a 4 millihenry can be selected for this I mean typically design. Well, selection of a ripple filter to filter out the noise from the voltage at PCC, the time constant RCC is less than let us say Ts, where Ts is the time period for the typically you can call it for the switching corresponding to switching frequency. So, considering RF CF equal to Ts by 10. So, RF is a ripple filter resistance and CF is the ripple filter capacitance and Ts the switching time corresponding to switching frequency. So, considering the switching frequency of 1.8 kilohertz, the ripple parameters are selected RF equal to 10 ohm and CF equal to 5.5 and impedance offered of switching frequency is 18.92 ohm and impedance offered at fundamental frequency 579.12 which is sufficiently large, hence the ripple filter draws the negligible fundamental current and certainly the losses in the ripple filter also quite low. Your high frequency current also will be quite low. So, selection of this voltage rating of this solid state devices IGBT of the DC STATCOM, I mean that we take VD that will be equal to VSW. So, it will be a sum of the DC link voltage plus VD, the 10% overshoot in the DC link voltage under the dynamic condition and the voltage rating of the switch is calculated as typically 770 volt with the appropriate safety factor. Normally for this voltage range of 415 volt line we consider 1200 volt IGBT we selected for the voltage source converter used in this DC STATCOM. Similarly, the current rating of the switches I mean we consider around with the safety factor about 25% 1.25 where we consider the peak current which is going to in DC STATCOM current plus the ripple current I mean like peak of ripple current. So, from these equations the voltage and current rating of the IGBT can be estimated and the current rating of switch is calculated 149.59, thus a solid state switch of VSC selected with respect to next available rating that is 1200 volt and 300 ampere like. And these are typical I mean you can call it the design calculated data I mean for a given rating I mean for 3 lakh VSC and 2 lakh VSC. So, DC link voltage I mean we can have 3 single phase if we take all 3 topology corresponding to the design. So, I mean considering even a unity ratio of the transformer in case of 3 single phase VSC, the DC link will be here only 350 volt where the 3 lakh VSC it will be 700 volt and 2 lakh VSC because each half should be greater than the line. So, it comes around 1400 volt like. So, that is another drawback of course of your 2 lakh VSC, the voltage rating virtually is almost the double like and that causes the typically the rating of the device is also affected. And DC bus capacitance we already calculated that for being a lower voltage of course in 3 single phase the capacitor value comes I mean like a 5000 microfarad and here it comes 3000 in 3 lakh VSC and 2 lakh it comes 3300 and the interfacing inductance of course in single phase it comes millihenry and it can be 2.5 millihenry for 3 lakh VSC and 6 millihenry for 2 lakh VSC and voltage rating of the switch for single phase it comes only 600 volt. Of course, it comes like a 1200 volt for the case of 3 lakh and for 2 lakh it comes 1800 and current rating of switch is 100 ampere I mean for typically for all the rating like. Then we like to go of course the design of 4 wire system 4 lakh VSC based DC STATCOM where we have a 3 lakh for 3 phases and the 4th additional lag we consider for the neutral. So, here is a 3 phase 4 wire supply system with the 3 phase voltage and the neutral and at the after the source impedance we have a point of common coupling where we are connecting the 3 phase 4 wire load. It can be balanced load, it can be unbalanced load. Well, unbalanced load even can be even a single phase or 2 phase. We can have a load even on single phase also, or all the 3 phases, and there may be unbalance in the balanced 3 phase or balanced 3 phase load also there may be there. Like, I mean, it can be reactive load or capacitive load, or even a pure resistive load may be unbalanced load, like, I mean, that we discussed in the previous chapter, like when we were discussing passive compensation. So, here we have again typically the 3 interfacing inductor for 3 phases, and then fourth lag we have another interfacing inductance. The value may be little different because here the ripple current is not decided with similar formula. Of course, the DC link capacitor is again for self supporting DC bus, and we will use the 4 lag BSC because of the fourth lag requirement here. And then we have a RC filter, I mean, here with the RF and CR, like, I mean, also. Well, this is the basic circuit. Here also you can understand, I mean, we will discuss in control, we have to regulate the DC link voltage, so that speed room, I mean, is quite effective to operate satisfactory to, you can call it to control these compensating current, I mean, which are ICA, ICB, IC also, or as well as ICN, like, I mean, also. So, ICN is very straightforward, the reference for this will be ILN, because you have to compensate that current with the opposite phase, so that ISN is 0. So, that is for other typically we will like to discuss with the control how we are going to have a reference supply current or reference compensated current. So, there are many concepts of as far as in control is concerned, like, so we will talk about the after the design about the control of this. So, here also the DC link voltage you can call it like is again 2 root 2 into VL upon root 3 m, where again modulation index and can be considered 1 or 0.9, and VL is the line PCC voltage. Thus, only one may obtain the value of VDC as 677, and we can select for this 400 volt it can be selected as a 700 volt after the round of values, like, I mean, also. Well, the DC link capacitor here usually it is a different formula than what we discussed earlier. The reason being here, I mean, typically the second harmonics will get reflected typically on the DC link, I mean, and because of presence of second harmonics on the DC link, I mean, we have to have a twice of the frequency, similar to like a single phase inverter circuit. That is the relation it goes. So, where I 0 is a capacitor current and omega 0 is the angular frequency and VDC is the ripple voltage in the capacitor, and considering the ripple 1.5%, VDC ripple of 0.0700. So, it is a 10.5 volt, and we can find out typical value of I 0 for a given of 50 kVA rating, and it comes to be like a 78.57. So, CDC can be calculated 11,902. 909.337 microfarad, and this can be selected as 12,000 microfarad, like also. Well, selection of AC inductor. So, the inductor for neutral lag we can select here. Typically in this case only the DC link voltage will be responsible, and 3 root 3 is corresponding to the neutral, because triplen will be there, and AFICR considering the 15% ripple and switching frequency 1.8 kilohertz and modulation index 1 and DC link voltage of 700 volt and A equal to 1.2, the neutral lag inductance is calculated to be 5.43 millihenry, and round of value can be taken 5.5 can be selected for this, like. So, the of course, for other 3 lag the formula remains same as we have discussed in typically 3 wire DStatCom, that is root 3 m VDC by 12 A F I ripple, and considering 15% again ripple 1.8 kilohertz and M equal to 1 and VDC 700, A can be 1.2 and LR can be calculated 4 millihenry. It comes around 3 point something. So, we can select 4 millihenry as a value for after the round of line. So, to find out the noise from typically the voltage at PCC because of switching of this voltage source inverter. So, again we can say that this time constant for RC filter should be much less than the switching frequency. So, considering this typically the value correspond to that. So, we can think about RF equal to filter resistance, CF is the filter capacitance and TS the switching, and considering the switching frequency of 1.8 kilohertz and considering typically resistance of R equal to 10 and CF 5.5, the impedance again for fundamental for the switching frequency is 18.92 and impedance offer at fundamental frequency is 579.12, which is substantially large, and hence the ripple filter draws a negligible fundamental current, and thus the reason the losses, because it will be very milliampere current. You can think about like even a I mean like you take a typically phase voltage 239 or 240 divided by 579, it is a hardly a you can call it a I mean 400 milliampere, and 400 milliampere you can consider the square of that will become a even decimal. So, you will have a losses hardly less than a watt or so, even in all 3 phases this will be summing all will not be more than 1 or 2 watt like or so, irrespective of the rating, because these concept are irrespective of rating, whether your DStatCom is 50 kV or 100 kV or 200 kV like common. Well, selection of the voltage rating of the switches here. So, again switch voltage rating should be DC link voltage plus the overshoot in the DC link. So, that is the highest voltage we have selected it, but there will be some overshoot, I mean because of the controller action around 8 to 10% overshoot is there. So, taking a safety factor of around 10% in the DC link voltage under dynamic condition, the voltage rating of the switch is calculated 770. The appropriate safety factor, we take a 1200 volt IGBT for the voltage source converter used in DStatCom. And this typically the switch current rating we decide again 1.25 with a kind of an I ripple peak and then the peak of DStatCom current. So, from this equation the voltage and current rating of IGBT can be estimated, and the current rating of the switches is calculated as 149.59. The solid state switch of VSC selected with the next typically available higher rating of 1200 volt and 300 ampere like common or so. So, coming to the typically another topology design for 4 wire system, typically 4 wire system, that is a design of 3 phase 4 wire DStatCom. So, we have a 3 single phase voltage source converter based DStatCom here, and what we are using here, of course, we are using a transformer, I mean like a for the purpose of isolation, and it can be for scaling the voltage level also, that may be the your load and distribution system may be at high voltage, but power electronics you can design at lower voltage, but when we discuss in principle of operation. And these 3 single phase, one of the major benefit that you can use the unipolar switching. So, ripple current frequency will be double the switching frequency of the devices, or other way you can call it switch. You can see here is half the switching losses in the devices will be lower in this case, and the DC link voltage can be maintained much lower, approximately half compared to what you have in previous topology like. And here again we keep RF and CF for mitigating the switching ripple here, typically at the point of common coupling like. Well, here because this typically working as a single phase inverter, so selection of DC bus capacitor is similar to like a VDC into root 2 V upon M, and M is the modulation index and we consider 1, and the AC RMS voltage of phase voltage of DStatCom. So, thus one may obtain the VDC at 338 for a, you can call it V 239.6, and it can be selected like a 360 or 400 like typical order of that like also. So, that is about the DC link voltage selection here, because it is similar to single phase. Similarly, the capacitance is also corresponding to, because second harmonics again they are on the because of operation of independent phases, and you might have a, because of unbalance the second harmonics appearing at the DC link. So, the same formula is valid here, I 0 upon 2 omega VDC ripple peak, and I 0 capacitor here, the where is the I 0 is the capacitor current, omega is the angular frequency, and VDC is the ripple filter. Considering the 5% ripple voltage of 360, so 18 volt, and I 0 for 50 kV if we are designing, then comes 138.88, and CDG obtained is 1200 to 86.7. So, it can be selected 12,500 microfarad like also. Well, the selection of interfacing inductance here again, because the formula it is like a single phase inverter or voltage source inverter. The formula of all ripple current of single phase will be applicable here. So, this interfacing inductance for the single phase voltage source converter similar to will be M VDC upon 4 AF FS I ripple current, I mean typically of peak to peak. So, considering 15% ripple and switching frequency 1.8 kilohertz, modulation index 1 VDC 360 and A equal to 1.2, LR is calculated 2 millihenry. It comes around less than little 2 millihenry, and we can calculate typically select 1.2 millihenry for this like. And coming to the selection of ripple filter, I mean to filter out the noise from the voltage at point of common coupling, time constant is again considered much lesser than RFCF as a time constant of the filter, where the RF is the ripple filter capacitance, CF is the ripple filter, typically you can call it capacitance, and TH is the switching, I mean the time period for corresponding to the switching frequency like. So, this is the table of summary of design for 3 phase 4 wire StatCom, the different topology, around 7 topology corresponding to the same rating, and you can find out that typically the DC link voltage here it is around 350 with the DC capacitance 6000 microfarad and AC inductance of 1.5 millihenry, and this is 3 single phase based, and what is the rating of 650 ampere current, and of course, no transformer. And we talk about like I mean similarly for other one and similarly 3 lag BSC with the split capacitors or you can call it the 4 leg VSC, that is important. So, you have a DC link voltage 700 and you have a capacitance of 4000 microfarad, that will reduce because the voltage is little bit increased compared to the, and then you have a inductance of 2 millihenry and voltage rating of 600 volt and typically of 50 volt, I mean like, and then 50 ampere, and then if you come out with the transformer isolation, of course, here it is we consider the transformer turns ratio 1, but not practice transformation ratio normally will be higher because you will be connecting this D STATCOM at much higher voltage than only the one of the reason that why you have to use the transformer for the purpose of, one is of course isolation, another is to interfacing the high voltage distribution system this, and you are designing the power electronics at optimum voltage like, I mean. So, it is a 3 leg VSC with the transformer typically, and all the parameters comes around the same with the transformer isolation for all the design like or so. So, we can have a typically control of this.